So welcome everyone. This is Nicola Marzari from EPFL, and it's my great pleasure to introduce Professor Dominika Zgid from the University of Michigan to give our 36th Distinguished Lecture for the National Center of Competence in Research, MARVEL, on Ab-initio Green's function methods for molecules and solids. What accuracy can we reach? Dominika is currently a professor at the University of Michigan that she joined in 2012. She earned her undergraduate degree at Warsaw University in Poland, and then a PhD from the University of Waterloo in Canada in 2008. Very broad areas of interest in the field of, say, condensed matter physics and theoretical chemistry, and very much at the intersection of the two. Her work includes designing new and systematically improvable computational methods to study strongly correlated molecules and materials, and she has worked and developed molecular versions of the density matrix renormalization group, solvers for dynamical mean field theory, conserving Green's function methods for weakly correlated methods, and Ab-initio embedding Green's function methods. That was actually the first time I sort of became very interested myself in her work. So Dominika, great pleasure to be here, for you to be here, and the floor is yours.
Thank you, Nicola, for the introduction, and I'm very pleased to be here. Let me share my slides so I can make sure that everything is working. All right, it is a great pleasure to be here. I will basically try to tell you about major research directions that we cover in my group. I will not go into anything in depth. It will be more of a review of what we are doing and what we are interested in. And I hope to cover a number of basically topics and that you see what my group was working on over the years. So as Nicola has mentioned, I'm very interested on the intersection basically of quantum chemistry and condensed matter. So in my group, we are primarily working towards basically reaching a very material specific, high accuracy type of calculations that I would say use a lot of quantum chemistry machinery, but many times, we are interested in condensed matter system and condensed matter methods. All right, so what are the challenges if we want to simulate realistic materials? I know that I'm preaching here a little bit to the choir, right? But if we really want to do everything ab initio, we would want to simulate, obviously, a material-specific way. We would want to do like strontium materials like strontium iridate. And for these materials, right, there is like a high interplay of electron correlation and relativistic effects. So one would assume that one could cover both of these effects ab initio. And obviously what one would want to do for many of these materials, one would want to simulate, let's say, pressure dependence, evaluate bulk modulus. This is especially, for example, true for relativistic actually materials, for actinides like fault-tolerant fuels, like, for example, uranium silicates, where people are interested in bulk modulus. And finally, as I told you, actually, I do not work on model systems. Like all the technology we developed could be applied to model system, but purposefully I avoid that to basically challenge ourselves to, to calculate actually the realistic systems. So we want to do it material specific for basically the real big problem. And the same challenges happens actually in molecules. Like this is, for example, a molecular magnet, right? So this yellow and red dots, these are actually the spin centers. And for this, basically compounds, the inorganic chemists usually want to know the temperature-dependent magnetic susceptibility. So obviously, in order to illustrate that, one would need to cover the interplay of temperature and correlation effects, and one would want to simulate the basically influence of temperature on magnetic properties. So for example, one would want to calculate the Néel temperature. So these are actually real computational challenges, and it's many times very hard to, to cover all of this because one has to deal with many effects simultaneously. So obviously one would want to illustrate correlation as much as possible, right? So one would want to cover both the weak correlation at some correlated method, like weak correlated method level, for example, like GW, but one also wants to include the strong correlation, right, at some embedding method, with some embedding method, at least for a couple of orbitals. One would want to deal with temperature many times, maybe not temperature that actually affects vibrations, but actually the component of temperature that really affects electronic degrees of freedom. Finally, for the systems really, to reach the realistic setting, one would model disorder. But I would say we did not yet move our development in that area, so I'm not going to tell you anything about it, but we did move it towards relativity, and I will tell you about basically including also relativistic effects, which we include at the two-component level. So see, in solids, obviously one would want to evaluate this as accurate as possible. So if one would use this quantum chemistry analogy, one would want a Green's function for the whole system. And that's obviously, one would want to have wave function for the whole system. And that's obviously like incredibly difficult task because one would need to construct what, quantum chemists call active spaces, right, for all these d electrons that are there. So that's like not actually possible, right, because we would need to consider that many determinants, and obviously we cannot do it that way, or at least at present we cannot do it that way. So that would involve very long multi-determinantal expansion, large number of basis functions. So there are, even though there are this, huge drawbacks of this type of treatment, there are also obviously some opportunities, right? So one can observe, and this is what actually is effectively used in condensed matter, that these d electrons are very localized, right? And there is some sort of, one can say, separation of weak and strong correlation, at least at certain level. And we obviously capitalize also heavily on this, that the energy is not the quantity of interest, right? So we don't evaluate the cohesive energy of the unit cell. So that gives us some wiggle room that basically the calculation does not need to get as accurate as in quantum chemistry, and one can perhaps, get away with methods that have somewhat lesser accuracy, even though one delivers the quantity of interest for experimentalists. So in my group, we are primarily, interested in the development of what are embedding methods, right, in order to cover this difficult system. So that allows us basically to divide the whole system into a part that is quite tractable, and we can describe very accurately while describing everything else, like the environment, approximately at some kind of lower level method. And obviously, we want to do it that way that the electrons, right, can exchange between this chosen fragment and the environment. So this is designed for open systems and allows also for the delocalization of basically this electron cloud or wave function to the environment. And these methods are undergoing very intense development, so there are many flavors of them, and I'm sure you have heard about basically many other researchers talking about it. So we are interested actually to develop Green's function methods, not wave function methods, primarily because this basically allows for direct connection to ARPES, right, which is experimentally what our colleagues are registering. So they usually come to us with this sort of ARPES diagram and would like us to evaluate both occupied and unoccupied part of the spectrum, right? And if one basically include all sorts of correlation, one can, from our Green's function methods, one can get this basically correlated Green's function, which then we can evaluate the spectral function from and simulate what they are asking us for, which is this ARPES spectrum. So in order to see, like, one of the basically big challenge is to make our calculation accurate, right? Like accurate to the level that I would say quantum chemists would be somewhat satisfied. So there are many components that one has to cover in this calculation. So one is the orbital representation, right? So we have to choose some orbital representation that would allow us to develop this accurate treatment. Because we use these embedding approaches, we usually would not want to work in plane wave and use vernier projection, because that's usually not completely, I would say, not without any ambiguities. So we want some sort of excellent representation of the orbitals, especially occupied orbitals, that we can derive just from, looking at atomic levels. So we also want a compact basis, not basis with very many functions, right? Because that would make our correlated calculations actually very expensive. So for that reason, we use Gaussian orbitals. So when we have some sort of weakly correlated method, right, that has to happen for this embedding problem. So we want this method to describe many effects. So we want it to be finite temperature. It has to be cheap enough so we can actually do like a big realistic system with a decent k-space sampling, right, decent number of orbitals in the unit cell. It has to converge quite robustly, obviously, right? And it has to have some good way of treating finite size effects and hopefully include relativistic effects. So in my work, we primarily use fully self-consistent GW and fully self-consistent second order for molecular problems. But obviously, many other groups, right, develop many other, like some sort of flavors of GW, for example, quasi-particle GW or G0W0 and so on. And then finally, right, there is this embedding approach that utilizes these two parts. And obviously, we have some sort of set of demands on what this has to be. But let me first tell you about these weakly correlated methods, and then I will switch back to this embedding. So in these weakly correlated methods, we develop all our methods in Gaussian orbitals. And these are Gaussian orbital implementation for solids. So the good thing is, right, that we have few orbitals. They have pretty good representation of atomic orbitals. And they can easily give some sort of chemical interpretation. We can tell, for example, what, I don't know, dz squared orbital or, dxy orbital is doing, right? How it translates into EG and T2G manifold. And the disadvantage is that basically one cannot so easily converge it to the basis set limit, like with plane waves. Like they can get linearly dependent, and they somewhat underdeveloped for solids. So if you look, for example, at molecules, and you wanted to do something with nickel atom, right, for molecular systems, I'm sorry, here it's for molecules, you have 200 type of basis sets optimized for nickel for molecular problems. But for solids, if you look how these bases were optimized, you have only 5, right? So there are very few choices, actually, what kind of basis set you can use for solids. And we try to remedy this. We introduce this material-specific optimization that actually we use it in our work. So you can see here that, like this is, for example, nickel oxide just optimized at the level of LDA. So this is a plane wave. This is a standard nickel oxide basis, right, that one could just load from a library. You can see that this unoccupied band is completely wrongly recovered. One can go to bigger bases. Does not improve. Only when one optimizes this material-specific way, right, one can basically get the good improvement of this unoccupied bands. And one can introduce this basically optimization of exponents and coefficients in this material-specific way. One can optimize the total energy with some penalties for orbitals getting linearly dependent, and one can actually get pretty good results. But this usually requires us to re-optimize the basis for the case we are working on. So when we kind of load this Gaussian basis, right, onto usually GW method for us. But since there are so many flavors, let me show you in which corner of this basically flavor array do we sit. So there are zero temperature GW methods, right? And historically, there were many approximations like plasmon pole approximation, for example, and maybe people were doing single iterations, but when there are also, right, like where you include methods where you include full frequency representation and you do many iterations, but usually you do it at the level of quasi-particle approximations, so you may evaluate only the diagonal, basically elements of self-energy, right? And that is done on real axis, so you immediately have the access to spectrum. So usually, right, one does not do full self-consistency in this approach. Usually one basically does a single shot type of iteration, and that allows to evaluate only a basically single iteration. Then there is the imaginary axis GW, which basically has, which we are using, right, which has multiple frequencies. And then one can also do a single iteration or many iteration, but it has to be followed by analytical continuation of basically this self-energy in order to get access to spectrum. One can do the single iteration or one can do many iterations, which will give this result independent of the starting point. So we are doing basically this fully self-consistent GW, where usually, right, we have to follow it by analytical continuation. So this is the part we are basically in. So how our fully self-consistent GW look, right? We do it in block orbitals. This is finite temperature. We do full self-consistency. We basically include all elements of self-energy, and we do this exclusively on this imaginary axis. So we do everything as written by Hedin, actually with no approximation when doing this on imaginary axis. And if we basically did it like as Hedin has written, right, the scaling would be as n to the sixth with the number of orbitals, right, and n squared with the number of k points. So that would be very expensive. So due to this, actually we introduce factorization, and we factorize the integral, right, which is this basically four-dimensional tensor if we discount for the dependence of k space, right? We basically decompose it onto two tensors that are all free-leg tensor, and that allows us to perform this GW with scaling, which is like n to the fourth. So you can think that this is basically comparable to what would be, right, Hartree-Fock scaling. We also have right now implementation where we factorize even better. We factorize that with tensor hypercontraction. So one can get even better scaling, which is like n cubed, right, which is very comparable to DFT actually. So we use this type of, right, decomposition in order to speed our GW. And that allows us to basically then also accelerate this on GPUs. So when the calculations get, pretty fast, and we can scale it to 100 GPUs, we can run it on our DOE machines. So that allows us to basically have like almost linear speed up with the number of GPUs. So there are other things that have to be taken into consideration in order to make this, this algorithm very well converged for all systems. So we also have some convergence accelerators, right, which allow us to basically converge the iterations, right, because it's done fully self-consistently. So what we do, we use basically a scheme called DIIS, so direct inverse subspace, which allows us to take the vectors from the previous iterations and accelerate the convergence. So you can basically see that for systems like silicon or bismuth vanadate, like you should look at this basically green and blue lines. One can reach convergence in many fewer iterations than just using a simple damping. So that is very, very important for many systems. and actually, you know, allows us to conduct these calculations efficiently. So then, right, it has to be followed by this, basically by doing some sort of analytical continuation, because our whole calculation is on imaginary axis. So we use basically Nevanlina analytical continuation. So that allows us to get spectrum, and that actually works very well. Like traditionally, these analytical continuations usually can be done only for peaks around Fermi level. So the first IP, for example, is very well recovered, but the IPs away from the Fermi levels, right, the peaks are not well recovered. In Nevanlina, actually, that is not such a huge problem. We recover many peaks even with quite good accuracy, even in the core. So you can see this is, for example, the IP spectrum of water. And you can see that even this sort of deeper lying peaks are recovered quite well. So finally, these are core data. And you can see that here, this is the XPS of basically carbon, where we, you know, try to recover basically like the 1s, right? The excitation from 1s core orbital, which normally would be very sort of hard to do, even though the systems are fairly trivial. And using like regular analytical continuation, for example, like the max end or maximum entropy, right, continuation. And here you can see that basically if we compare the Nevanlina to PADE, for the systems, you can see that the error in EV is actually very small for Nevanlina for this analytical continuation performed for the core orbitals. So that basically allows us to almost exclusively carry out our weakly correlated calculations on imaginary axis and then continue them to real axis. So how this, you know, the fully self-consistent GW, this is actually not done by many groups. Usually people do a single shot GW or some kind of version of self-consistency, how this compares to these other flavors. So this is basically comparison, like a very standard comparison for band gaps of semiconductors. So you can see here, right, that these are very standard semiconductors. But what one can very well see that this fully self-consistent actually calculation is very similar to the quasi-particle self-consistent calculation of Shilfgard-Kotani. So it basically gives almost the same results. Obviously, it can be worse when the G0W0, if the reference of G0W0 is chosen to match the experiment. But if we didn't know the experimental result, right, it's not always that easy to choose the good reference. For example, if these results were done based on Hartree-Fock reference, they would be very different. So for us, right, all this fully self-consistent GW is completely reference independent. So we can converge it very well with the basis set, actually. And we can also converge it with respect to finite size effects, where basically we developed this very robust finite size correction that we, even with small sampling of basically momentum space, we can get very converged result. All right, so that allows us to do basically this GW with cost, which is n to the fourth. And our imaginary time grids are actually quite efficient. We use the intermediate representation grid, which maybe has here around basically 80 or from 80 to 150 points. This can be very well parallelized, right? Because each grid point can be done on separate GPU. So this leads to actually calculations that can be quite sizable that one can do at the level of this GW that can underline this whole embedding machinery. So that obviously also removes all the reproducibility issues because, for example, we can, be reference independent. So it doesn't matter if we start our calculation from PBE 0, PBE, or LDA. And this basically GW framework can treat around 300 orbitals in the unit cell, with the newer factorization even around 600 orbitals in the unit cell. So that allows us to do like actually quite sizable systems. All right, so see, but if one wants to really calculate, right, something like strontium iridate or any of these compounds that right now inorganic chemists are synthesizing, one has to introduce the relativistic effects actually. So we did that, and we introduced the relativistic effects at the two-component level. So what that means, right, like the full Dirac equation would be at the four-component level. So that is way actually too expensive usually to do, and perhaps not fully needed. Obviously, that has full coverage of all spin-orbit coupling effects, but we want to have something cheaper, so we do this two-component calculation. So that means we do not explicitly treat the positron degrees of freedom, and this is some kind of minimal formalism to describe spin-orbit coupling. So the advantage of this formalism is that it doesn't change actually the two electron integrals, so it's very natural to basically connect it to embedding theories. So this is including spin-orbit coupling, not to the full extent, but basically like it's included right with some errors, but still one has this basically inclusion. So what one does, right, in this X to C1E, one starts from the four-component Dirac Hamiltonian, which is basically the kinetic Hamiltonian. One does the transformation to two-component approach. And then that allows us to get this basically two-component Hamiltonian for the kinetic part. And then one can fully construct the two-component Hamiltonian that has both the kinetic part, which includes all these relativistic one-body effects, plus some description of spin-orbit coupling, right? And then one has the non-relativistic Coulomb integrals, which basically are here, right, the two-body part of the Hamiltonian. So in that way, one can work with ordinary two-body integrals with, only modification of this one-body part, right, which basically has this X to C1E Hamiltonian. So in that way, we basically calculated with GW some correlated solids, which require relativistic treatment. So for example, this is silver bromide, so it's heavy enough that there is some relativistic effect. So see, this would be the non-relativistic spectrum for the silver bromide. If one adds basically the what we call spin-free approach, right? So this is like a simplified approach where one doesn't fully account for spin-orbit coupling, but one basically accounts for effects that are connected to much heavier core. So one sees that basically the unoccupied band shifts down, right? Nothing much happens to the occupied band. And then when one does this full two-component approach where one still accounts for spin-orbit coupling, you can see that there is the splitting of basically p orbitals to p3 halves and p1 halves, which is the right, which is introduced due to spin-orbit coupling. So the same can be done for silver iodide, and right, you can see the same effects that basically the unoccupied band gets shifted just due to inclusion of relativity. And then here, right, the magnitude of spin-orbit coupling is much greater, so one can see the splitting of the bands. So we can, again, converge this with the basis very nicely in this approach, and we can basically, right, like illustrate all the finite size effects, so one has a converged result with respect to the number of K-points. So obviously, this is like a good step, right, into direction of including all this relativity and getting these calculations fully under control, where one gets basically high accuracy, right, even for these difficult systems. But how does this actually work if we want to, to see it versus other methods? right? So if you look, for example, here, it's actually kind of interesting, you know, how fortunate DFT is. All right, so if one does DFT non-relativistic, right, you can see that it's sort of very bad in comparison with experiment, but when one includes relativity, it gets much worse, right? So it was sort of good due to some kind of fortunate error calculation. Then when one does, right, like fully relativistic, fully two-component description with DFT, it gets even worse. So this is the non-relativistic GW, also pretty bad, right? The spin-free GW gets closer to the experiments, and the fully relativistic GW gets even closer. It's not yet at the level of experiment, right? This can be either due to the basis set, or there is more correlations to be included than in the GW itself. But basically, one can see that this is like a step in a good direction to recover the right answer for the right reason from basically ab initio method that is including both correlation and relativity. All right, so in this fully self-consistent GW, right, the energy is uniquely defined because it's a conserved method. So one can evaluate energy either through thermodynamic integration or directly from Galicki-Migdal formulas. They all give the same answer. So this is very important because that allows us to calculate this energy in without any ambiguity, right? And without any dependence on the starting point. This usually is highly accurate and can be compared with other methods. And we use that, for example, to evaluate the bulk modulus. So how this bulk modulus, you know, looks like in GW, like what accuracy one can reach. So this actually is pretty non-trivial calculation because one not only has to get the equilibrium geometry right, one also has to get basically the curvature of the curve right. And it gets actually fairly difficult many times because one has to deal with a lot of linear dependencies in the basis, especially when one gets to this squeeze region. So even though, you know, it looks like a couple of points calculated, usually this is actually quite serious calculation. So see, this is how basically we can calculate, for example, something like the errors in lattice constant from the GW and other methods. And these are, you know, somewhat simple systems, right? But still relativity plays a role for them. So you can see that basically this error in the lattice constant, like we have two types of treatment, right? We basically have PBE, either all electron or with GTH basis. And you can see that the PBE, which is all electron or with GTH basis, they all give actually pretty similar results and are pretty good. So see, right now we have the fully self-consistent GW with the GTH basis. So you can see that actually something interesting happened, that actually when one does the GW usually with the core treatments, it's not actually that good because the core is developed for DFT, not GW. So you can see that the errors actually are worse than DFT if one uses this core. But when one does basically then this is right like smaller bases, SVP, and bigger bases, and these are all electron calculation. When one basically uses all electron calculation and relativity, one can see that actually one can get more accurate than the DFT approach, right, with all electron and relativity. So I would say that this is trend in good direction. So see, these errors are very small. Actually, like there is not much to talk about. This is more of an academic exercise. But how does it look for bulk modulus? And see, for bulk modulus, you can see that right now, right, the DFT errors are actually pretty big. So the DFT errors are like the whole bulk modulus, you know, would be of order 80 here. So the DFT errors of 20 would be like a quarter of the value of that bulk modulus. So it's actually very sizable. And when you look at these columns, right, when actually one does all electron GW with inclusion of relativity, one can get to an error of basically around 5, right? So this is like around 3% of the total value. So one can get very, very sort of good and controlled error for bulk modulus for these heavier elements. So basically here, right, what we can show is that using basically this proper method leads to very controlled accuracy, and inclusion of relativity actually is very important for most calculations of this bulk modulus. All right. So I told you that we can actually evaluate energy from GW. This is actually, while from G0, W0, for example, one can evaluate energy, right? It depends on the reference usually a lot, and it would depend on the way of evaluating GW. Like if one evaluates from Galicki-Migdal, one would get different result than, for example, from thermodynamic integration. So this unique way of evaluating energy allows us to basically calculate quantities, for example, like Néel temperature in a unique way. Right, so Néel temperature is basically a temperature below which the states or the spins are ordered. And one usually has some sort of antiferromagnetic ordering, right? And above this Néel temperature, basically the spins are disordered, so the whole system appears paramagnetic. So to evaluate this Néel temperature ab initio is actually really non-trivial task. So most of the evaluations that are in the literature are done for model systems when one can get pretty good results, right? Because it's somewhat simpler. But for truly ab initio systems, one only does usually these evaluations with DFT on periodic systems, and these results actually are not very good. Usually they don't even illustrate the trend. So what we will attempt here is to basically evaluate a trend in Néel temperatures for a series of oxides. So we will have nickel oxide, cobalt oxide, and iron oxide, right? And we will try to see if we can recover the experimental trend. So actually, the experiment is here, I would say, I don't want to say not perfect, but there are actually many experimental values. But what you want to see is that basically, right, like the nickel oxide temperature has this highest Néel temperature when there is cobalt oxide and when there is iron oxide. So, so what we do, we basically try to evaluate explicit model Hamiltonian, but how do we construct it, right? So I told you that we don't do models, so how we do this in this case? So we basically calculate the energy of a unit cell in the systems, and we calculate the energy of the singlet and energy of the triplet, right? So the singlet will basically have spins, right? Like the triplet will have spins that are oriented this way, right? And the singlet will have basically the up and down type of antiferromagnetic ordering. So we have these energies, and that allows us to find the J1 and J2 coupling for this model Hamiltonian. So this model Hamiltonian is then only used in order to, to go to the thermodynamic limit. And we use basically like a cluster expansion in order to fully then find the temperature. And if one does this, you can see that basically the GW can recover more or less this ordering, right? That the nickel oxide has the highest Néel temperature when there is cobalt oxide and when there is iron oxide. We give a couple of values because this is like, this sort of high temperature expansion is done in, gives us different polynomials, and depending on the order, we can get slightly different values, but nevertheless, the trend holds. And we can, for example, if one does this at the UHF level or the DFT level, you can see that this trend is not preserved, that the cobalt oxide does not differ from iron oxide. So we can compare this to evaluations done in quantum chemistry on clusters, not in solid, right? So one basically cuts out a cluster and one believes it is big enough in order to evaluate this. And you can see basically that for this cannot be done for all sorts of oxides because they become progressively more complicated, and one cannot basically cut out a cluster and, you know, appropriately terminate these bonds in order to illustrate our effects. But for nickel oxide, you can see that this GW is comparable to basically DDCI2. It's kind of cryptic a little bit. What does it mean, right? But basically, this is a level of theory that is a composite method that is actually quite accurate. So one can, right, illustrate even these difficult quantities as Néel temperature. All right, so I told you a little bit about GW, but I want to tell you still about embedding. So, right, so this GW is used as this sort of bottom layer for embedding, and we use it because we can then with GW make this full method theoretically well-defined and systematically improvable. So we want our embedding to define in such a way that we basically pick the smallest strongly correlated subsystem, and we want it to carry it out, right, like accurately enough so we can compare with experiments, not just trends, but like the actual values. So what we do, we use a method that we call self-energy embedding theory, and we use GW as this bottom layer and usually exact diagonalization to solve impurities. This is a method that is analogous to DMFT. It differs by basically a couple of steps only, and I will try to tell you like shortly what we do and what are the differences. So obviously, right, other people use all sorts of other methods like DFT plus DMFT, G0W0 plus DMFT, and so on. So, right, like if one writes the Green's function in solid, one could write it in such a way that basically one has a Fock matrix, right, for all k points, and then one can define that we are interested, obviously, mostly in some sort of strongly correlated center. So one has self-energy for the d orbital plus the self-energy for that, right, orbital that comes from all the rest of the crystal. So this is what I denote here as the sigma rest. And right now, right, we can basically do nothing fancy. We can just do the Fourier transformations to the real space. So we can transform the whole Green's function, self-energy, right, the Fock matrix, and finally we can get the Green's function in the real space with exactly the same separation, right, that we have the self-energy of the orbital and the self-energy of the rest, right, which basically is the self-energy, or you can think interactions coming from all the other orbitals that are influencing, right, our d orbital, basically. So what is happening, right? Usually we are interested not in I mean, we may be interested, but what we can do is, right, we usually can calculate the properties of the unit cell only, and, you know, maybe not the whole chunk, right, not the whole crystal, but we are interested in some sort of local properties. And what that means that basically we can rewrite right now our Green's function, right? Like this one was basically the Green's function for the whole crystal in the real space, but we can rewrite our Green's function truncated to the cell, right? So this is basically the Green's function of a cell when we could write this separation onto the Green's function of some sort of correlated orbital and how the rest influences this orbital. And when we have appearance of the single term, which is called hybridization, right, which arises because basically right now I perform this truncation to the cell, and here I explicitly wrote this Fock matrix Hamiltonian of a cell plus the self-energy of a cell, right? But they are influenced by the inversion actually of the whole matrix. So this hybridization arises because the inverse of a subset is not a subset of an inverse, right? So basically mathematically it arises due to inversion of this whole problem, but here I'm only inverting, right, the small problem, so I have to add this basically in order for these two equations to be equivalent. So one can also have, right, like a physical interpretation that this hybridization is basically how the rest of the crystal is influencing our unit cell, but it has also this clear mathematical interpretation. So at this point, right, everything looks very similar to DMFT. And but one has this sort of separation of d orbital and the rest. So right now, what we do, we can rearrange the term, right? And in here, basically, the Green's function of this correlated cell will be defined as the Green's function inverse of the d orbital plus the self-energy of the rest, right? And then we take the whole inverse. So that's actually a little bit different embedding equation than DMFT, right? Where we would say that this Green's function of the cell is equal to the Green's function of the impurity. So here it's not quite. One also has this self-energy that surrounds it. And then, right, we introduce this auxiliary problem that basically is, right now, the Green's function of the d orbital, which has the self-energy of this d orbital, right, minus the hybridization. So this part we need to evaluate, right, by introducing this basically impurity Hamiltonian or the auxiliary system, where we surround this d orbital, right, by some sort of one-body buff. So this d orbital here is surrounded by this one-body buff, right? We can write this Hamiltonian explicitly. And we can basically, so this is a very simple Hamiltonian, right? It has the one-body Hamiltonian of basically the d orbital, right? The two-body Hamiltonian of the d orbital plus the coupling to the environment, right? Which is only one body. And this can be solved. We solved that with basically ED or configuration interaction. Physicists like to solve this by Monte Carlo methods usually, so they don't have explicit buff representation, right? But the buff can be integrated out, so it's implicit, and one evaluates the Green's function of the d orbital. So what that basically lets us do, right, which it allows us to split this system which has some strongly correlated orbitals embedded into weakly correlated environment, which may be by itself intractable, right? If we wanted to calculate it brute force, it allows us to split it into this series of manageable calculation where we do usually GW for the whole problem, right? So this is our fully self-consistent GW, the low-level method. And when we solve this basically impurity problems, right, for every single of our other orbitals that we want to treat at basically correlated, like, or more correlated level than GW, right? So the GW is cheap enough for solids, and this d orbital is usually solved for us at the ED level. So that usually is not, you know, a huge calculation, because this is usually like, depending on the manifold, right? Either two orbitals embedded in a buff or three orbitals embedded in a buff if we have the EG to T2G splitting. So usually this is around 20 orbitals, so it's also doable. So right, how the whole system works. So we have the full, basically solid, we solve it at the GW level. Then we can choose the strongly correlated orbital, either looking by occupation numbers, so that's actually usually done for molecules, or just by looking at the atomic characteristic of the orbital, which we do for solids. We solve impurity problems for this chosen orbital, right? We set up the whole self-energy from these fragments. This is why we call it self-energy embedding, and when we iterate till convergence. So we have actually worked on that for a long time. If you are interested in seeing how accurate this is in comparison to other condensed matter or quantum chemistry methods, these two papers really show that this can be as accurate if done correctly as CAS PT2 or even some DMRG, and it's absolutely as accurate as other embedding methods used in chemistry. So let me show you some sort of solid calculations that we have done. So one of them was done on strontium manganate. So this is basically like a, it's a component of ceramics, but we don't use it really in this sort of applied manner. We use it rather as a test fly of this, as a test for the embedding methods, mostly because we know that basically the GW plus EDMFT is failing to recover the paramagnetic insulating phase for it. And we know that the antiferromagnetic phase is well illustrated by all methods, right? We know that LDA plus DMFT can do it, but they have to manipulate with the basically parameters in order to get this to agree with experiments. So this is not like a straight plug-in calculation, but it has to be adjusted. So what we know is that basically the G0W0 gives a metallic state for this system. So at this paramagnetic phase. So this is definitely wrong, inconsistent with experiment. And we know that GW plus EDMFT also gives this metallic state. So we would want to know, right, if we can do it any better. We want to understand the origin of this metallicity, and we can right, try to formulate our version of this type of embedding and see if it can improve anything. So what is happening here? So see, we use this, so we basically first do GW on this system, right? So we use this temperature, which is definitely above the Néel temperature. We do the 6x6x6 crystal lattice, we do this paramagnetic phase, right? And we have a Gaussian orbital basis. These dashed lines are the experimental lines. And you can see that basically when one does this and when one when one does GW and one then separates the contributions according to different orbitals, you see that there is obviously this peak, which comes into a gap, which shows the metallic character, and this is mostly due to manganese T2G orbitals. So fully self-consistent GW gets drunk, any other versions of GW2. So this is actually a very pathological situation because it means that our embedding calculation has to start from this, totally wrong point, right? So what we do is we do single shot GW when we do embedding, and we iterate again single shot GW and embedding. In these conserving methods, it shouldn't matter if we do fully self-consistent GW and then embedding and then GW, or we do it that way. But in this way, it allows us to not to have fully basically wrong orbitals as the starting point. So you can see that, like if we zoom in here onto the gap, you can see that as a function of iterations, basically the gap opens. So in this 23rd iteration, there is still some sort of density of states in the gap, but once we iterate further and further, right, when we basically open the gap. So this is the total energy, the correlation energy. It converges slowly, actually, like, I'm showing this to show that this is actually a difficult system. It converges slowly, but eventually you can see that we can actually achieve a very good agreement with experimental spectrum. So this is right back, these dashed lines are the experimental spectrum. This is basically this 3 different colors are our results, depending what kind of impurities we include. If we include only manganese T2G, or also, for example, oxygen p-pi orbitals. And we can assign these peaks, right, from which basically orbitals they're coming from. This agrees very well with experiment. So if we analyze then the natural occupations in the unit cell of GW, right, in the gamma point, then you can see that basically the GW itself really gives this kind of metallic character that things are occupied and then only very partially occupied, right? But there is no like a strongly correlated part here visible. And in the self-energy embedding, you can have the basically almost occupied orbitals when you clearly see this T2G manifold, right? Which is basically strongly correlated, only very partially occupied orbitals, right? And the unoccupied part. So this basically allows us to, to do these calculations in a fairly controlled manner, in a very, without, right, adjustable parameters. So here we still knew the experimental results, but here I have like a system which is bismuth vanadate. which experimentally is the last of the vanadate family that was not synthesized. It wasn't synthesized because at ambient pressure, when they try to synthesize it, it almost immediately decomposes onto metallic bismuth and vanadium oxide. So what they do, they synthesized is a diamond cell. And the system is very interesting because they predict that it will be antiferromagnetic, but metallic. You know, most antiferromagnetic systems are actually insulating, right? So this is like a nice discrepancy that people want to see if this is really true. So this is a pressure versus unit cell size curve. And we know that there are two phases. Most likely there is a phase where in one plane spins are up, in the other down, or like this phase C where they are diagonally, like one plane this way and the other plane this way. Right? And the question is, when it becomes metallic, if at ambient pressure, it's actually insulating or metallic. So this is a very difficult calculation if one cannot take out this from this diamond anvil, right? Because any DFT will give two metallic. So one cannot very easily actually predict it by like traditional methods. So see, this is like the high pressure, like this is the lowest basically experimentally obtained pressure. And this is the DFT at PBE0. We have here the correlated result, like these peaks are not sharp because we use Van Lena, so it adds like a lifetime to the peak, right? So it naturally produces this sort of non-sharp characteristics, right? So we can see that here basically at this, the A phase, right, which was this phase where the spins were in this sort of up and down plane. The PBE0 actually is very good approximation, and the GW gives very similar result, and so does embedding, right? We basically see that this is a metallic type of system at this lowest experimentally achieved pressure. So then in the C phase, the DFT still gives us this metallic result, but see, the GW actually gives something qualitatively different. We have here some semi-metal, right? Actually, or almost metal, but of a different character, right? So this is like truly metallic. This is just semi-metallic solution. The same is with embedding. So the C phase definitely is not a metallic phase. It's some semi-metallic phase, at least according to our calculation. So see, they did not fully depressurize this cell. So we did this by basically computational methods where we extrapolated and depressurized it. And you can see that when the C phase in this fully depressurized regime, nothing changed, right? It's still semi-metallic, but in this A phase, the DFT gives something completely kind of metallic and crazy. But in our calculation, you can see that there is a tiny band gap opening. It's very small, obviously, right? But one can see that basically there is some very weakly semi-conducting, right, character building up due to the band gap opening. All right, so I hope that what I told you today is that this embedding calculations, right, and GW can be used for realistic setting in this material specific way, in a fully controlled way, and with presumably achieving some high accuracy due to our introduction of all these controls, right, and the kind of quantum chemistry language into some of these methods. And I would like to acknowledge all my group members who worked on that over many years. Actually, it took us many years to develop these theories to this level of accuracy, and the granting agencies for actually paying us to do so. And thank you for inviting me and listening.
Thank you, Dominika. Great pleasure. And I think I also personally love, this push of, higher order theories, but, applied to materials and to relevant materials. That is very much also the theme of what we do here. So we are open for questions. We have multiple ways by which people can ask questions. Everyone will see either a question and answer panel, and so they can just type it. or if they prefer, they can just raise their hand. There is a raise hand table tab, and then I think I can promote the person as a panelist, and so they can then speak directly. So I see a set of questions in the question and answer, so maybe I'll read them. And again, if people want instead to ask questions live, please just raise your hand. So from Qinglong Liu, it says, Dear Professor Zgid, thanks for the great talk. I have 3 short questions. So the first one is about the Nevanlin analytic continuation technique. And is asking, is it also suitable for 0 temperature GW, or is it only for the finite temperature GW?
All right, so the first question, so usually the 0 temperature approach is done on real axis itself. So you would not use any analytical continuation, but one could kind of come, what I would say, somewhere in between, right? 0 temperature and finite temperature, and do any not just GW, any Green's function method on the shifted contour, right? So that is like you neither on the real axis or imaginary axis. So then one could use the analytical continuation and this Nevanlin to do it formally. We didn't work on this to basically like adjust it to that approach yet, but one definitely could. So see, also I want to mention that all these Nevanlin approaches, right? Like they are connected with like well-defining the domain of Green's function. So I could imagine that even if you have a Green's function on real axis, which is 0 temperature, you could use this Nevanlin if, for example, the Green's function somehow was evaluated by some method that it like leads it out of, proper mathematical formulation or domain. So what I mean that like if it was non-causal, maybe you could causally project it. But this is speculation. I would say I'm standing 90% behind this, what I said about this. All right, so the second one.
I have to confess, it's the first time that I myself hear about this. So I went to Wikipedia to look for Nevanlin, because we are very also interested in sort of meromorphic functions. And I mean, at the end, it was very surprising the difference that you got in accuracy from the Padé approximant and the Nevanlin, and without knowing anything about it, and I'll study it. But do you have a sense, or is there a reason for such remarkable difference?
So like Emmanuel does not, I would say, I think in this first paper, they do not say exactly right to why. When only in our group, we actually investigated that for a real system, how well it works, right? They didn't. But so that's not yet published, but I think the difference is, see, it's a projection within, like respecting this Green's function domain. So I think that automatically gives you much more mileage. So we have other results, which I would say at present, I cannot truly explain. I don't know why exactly this happens, but I suspect that this is due to respecting this domain. So I know, for example, see in this tensor, like in this THC decomposed way, right? Like where we use tensor hypercontraction, we implemented the vertex in GW. So we're going to post that on arXiv very shortly. And there, the surprising thing is that, for example, like there are these papers about electron gas that the spectral function becomes negative. We never observed actually this negativity of the spectral function, but we suspect that this is really due to the Nevanlin continuation, which projects it onto this sort of proper domain. So I cannot yet explain it, but it really works in some sort of pretty miraculous way, I would say.
Interesting, very interesting. So a second question is, how important is the temperature in finite temperature GW? For example, does it change the ionization energy a lot when you change it?
So if the system is gapped, right, when the finite temperature, unless you above the temperature that, right, is that would promote things above the gap, will not change a lot. So for gapped system, and that also touches on your third question, right, for some small molecules, the finite temperature is actually irrelevant. It is just a mathematical trick that allows us to converge the self-consistency very well because Green's functions are smooth.
Okay, because I should read actually the third question because only us see it. So does the finite temperature GW method works for small molecule? I mean, there might not be enough electron in this system, and so not enough to be considered as thermodynamic equilibrium system in the grand canonical ensemble Green's function.
So it does work well. Like I would say we have a paper about comparison of different vertex version of GW and Fourier consistent GW for small molecules on arXiv. So it does work actually very well. One can get very accurate energies and very accurate IPs for small molecule. I would say it works better for small molecules than for solids actually. But for any gapped system, this finite temperature will not have much of meaning, right? Because usually you are studying this at temperatures which are below the gap. But for metallic systems or something that has a very small gap, it obviously will be crucial to be able to include this sort of electronic degrees of freedom, right, and treat temperature there. So for any of this, like if, for example, like one of the systems we currently work on is uranium nitride. So this is a metallic system, which basically is one of these fault-tolerant fuels. So when the temperature of the GW and of the whole calculation plays a large role. Even for small molecule, right, this is just irrelevant, usually is gapped. Temperature is not the question unless one, I don't know, is in a sun corona or something like that.
Thanks. Let me also, we have a live question from Mario Caserta. So I think Mario needs to unmute and then he can ask the question himself.
Hello, can you hear me?
Yeah.
Okay, thank you a lot for the talk. Sorry, could you eventually go back 1 second to the, I didn't get the methodological difference for the strontium, for the paramagnetic solution of the strontium manganate problem between, let's say, what is the difference between the GW plus extended MFT and your self-energy?
Okay, so let me come back here actually. So I think that seeing the strontium vanadate, like the results will not maybe help you, but let me get here. So see, all right, so basically, see in GW plus DMFT, what is happening, right? Like this equation in GW DMFT would read that the Green's function of the correlated cell is the Green's function of the impurity. Okay, so this is not, so this rest here is is explicitly included to the impurity by introducing the basically, right, by introducing the screened interaction W. So what happens, right, like in your impurity parameterization, you have to have screened interaction in GW plus DMFT, right? Because this rest term is not appearing here explicitly, is introduced through the screened interaction. So what does this do on this system? See, so if I get the metallic solution, and I would, for this metallic solution, calculate the screened interaction, right, the W is wrong, basically. So I'm putting this wrong W to the solver, right? The solver will give me the solution for this wrong W. So I cannot escape this sort of curse that my GW was wrong And therefore, right now, I get a wrong result from the solver itself, right? Even though I keep plugging it back, it wouldn't help me the way this is formulated. Like if one, I think, released all possible self-consistencies there, maybe yes, but not the way this is formulated like right now. So the difference for us is that, see, the sigma rest comes from GW, but the parameterization of the impurity itself is in unscreened interaction. So the impurity itself in unscreened interaction gives me right now something what, is wrong in the first iteration, but then, like, or maybe not wrong, but still not accurate in the first iteration, but I update the sigma rest, but my two-body interaction in the impurity is the true, right? Unscreened interaction all the way. So the sigma rest here screens it, but I do not, right, do it through basically the screen W. So what this means is that in the first iteration, when I started, it was metallic. Let me, here. In the first iteration, when I started, it is metallic, but because my impurity right now solution improves it, because I'm not using the screened interaction with this wrong W, right? Then gradually this band gap will open. So if you actually will look up like many of these GW plus EDMFT papers, like you will see a persistent problem that usually if the GW result at the beginning will be qualitatively wrong, they cannot recover the good result. They will improve if the GW result is somewhat incorrect, but not, qualitatively wrong. Because this can be traced to that right, this qualitatively wrong result gives them wrong screened interaction, which the solver takes, but when the solver, right, just takes it, cannot improve it. So in here, right, what is the difference is basically that this part comes from GW, this part is done in the solver, but the solver has unscreened interaction. So they like 2 Coulomb unscreened, right? Like I'm not changing them in any way. So then gradually this part will improve by taking feedback from the solver, but it's even though it was wrong at the beginning.
I see. Thank you.
Thank you, Dominika. A question from the question and answer pane from Xing Wang, and he asked how the Néel temperature was determined, that is, at which level of theory once you computed the exchange parameter, say, for the transition metal monoxides.
So where are this? So basically, you calculate this J coupling. We calculate this J1 and J2 from this fully self-consistent GW, and then there is we use this. If you read our paper, which is the Pavel's paper here, there's basically this JCTC paper. We'll use this method of basically French people where they have this long expansions, right, and of the effective Hamiltonian, like some sort of, so they put the spins onto the whole solid, and then they use like a high temperature expansion actually of this to evaluate, right, like a ratio of the polynomials. But I would say that this, the evaluation of the ratio of the polynomials and so on, it's not our idea. I deeply encourage you that you look here and look up basically all the references where how this effective Hamiltonian is plugged into their expansion.
Thanks. I think, while I was listening to your talk, and, because you say that you are somehow the intersection of theoretical chemistry and condensed matter physics, I have an almost philosophical question about correlation and localization. That is, if you want, you could say that the chemists don't have to worry about localization because they work with molecules, and they almost embed in energy. If you think at something like CAS SCF, you choose your active space, and you mix that up, and it's embedded in the rest. In a solid, we have all this idea of a strong correlation being local, and indeed, the Green's function is the embedding potential on a localized subspace. And it's really a question for which I have no answer. And I was wondering, are the strongly localized elements, the strongly correlated elements always localized? If I think at solid and impurities, as I go from deep impurities to shallow impurities, I get more and more the localized states. And so I wonder, could it be that we actually make an error sometimes in considering, correlated and strongly localized as being the same thing, or if you wanted, the correlated manifold being built out of localized objects? And I don't know if you have an opinion, an idea, or an experience. Yeah, so please go ahead.
So yes, so in molecules, definitely, I would say the strongly localized is not the same as strongly correlated. So in molecules, we use the embedding almost exclusively in natural orbitals, and the natural orbital is delocalized. It's embedding in energy, and this works actually amazingly well, I would say.
Yeah, but I would, without experience, I was more worried in the solid that if you have delocalized states, that would be very important to be mixed in the sort of whatever configuration interaction sort of.
So in solid, it's actually, very interesting, because we try to do this in the natural orbital. Our first time we did embedding for nickel oxide, we tried natural orbitals, only to discover that it actually works terrible. Yeah. So we never, you will not see us publishing this ever, because the result was so bad that it did not, couldn't come as, as anything, right? But so in solid, definitely, I would say this localized orbital is better. But I look at that maybe somewhat like, I would say, it's, to me, it's more like an artifact of how the embedding is defined. I'm not sure if I see this as some sort of very physical process. Because basically, right, like when we embed, like the same self-energy, or the same sort of, right now, the same way of formulating orbital has to, right, be transported to all the K points, right? Basically, like mathematically, right? We have to plug in the same thing for all the K points. So the orbital that changes the least in such way will be the atomic orbital. So, so in solids, to embed, these atomic orbitals are actually the best. But I think that this is like a, how the embedding construction is defined artifact. So Nicola, I agree with you that I'm sure that there are some states near the surface that are basically very delocalized, and this approach will completely break down. That I think that it's just only working, very well if we consider like D and F orbitals, which basically are not very modified, right? Like between the K points.
Yeah.
So, but if we wanted, I think, like to do the same and treat a surface state, no, it wouldn't work.
Okay. Yeah. No. Thanks. I think I understand. Okay. I think this probably is a fitting end to this distinguished lecture. Thanks a lot. I think we all enjoyed, and was very instructive. And as you know, it's recorded, so everyone can sort of watch it also later. So thank you on behalf of everyone, and thanks to everyone that was online and then in the different conference room.
Yeah, thank you so much. And thank you one more time for inviting me.